Hello and welcome to this webinar, Putting It Together, the SAFEXPLAIN platform and toolsets. This is the third webinar in our SAFEXPLAIN webinar series. If you missed the last two webinars or want a refresher of the content, please visit the video and demo section of our website. It's under the results tab. Before we begin, I'd like to inform you that the session will be recorded and will be made available in the coming weeks on the website. So also, we really encourage questions. Please use either the Q&A option or directly in the chat, and I'll be monitoring them, and we'll make sure that the speaker has access to the questions by the end of the session. So today's webinar includes presentations from two speakers. We'll start with a short overview given by the SAFEXPLAIN coordinator, Jaume Abella from the Barcelona Supercomputing Center. And this will be followed by an in-depth presentation of the toolset and platform by Enrico Mezzetti, also from the Barcelona Supercomputing Center. So Jaume Abella is the co-director of the Computer Architecture OS Interface Group at the BSc, and his main research interests lie in the timing and functional verification of critical real-time systems, with an emphasis on automotive, avionics, space, and railway domains. And Enrico Mezzetti is an established researcher from the BSc, and he holds a PhD in computer science on software timing analysis and industrial development processes from the University of Bologna. And he is the author of more than 60 publications on the verification of critical embedded systems, specializing in timing characterization and analysis of multi-core systems, RTOS, and software architectures. So we're in good hands. So without further ado, I'll give the floor to Jaume Abella.
Thank you. Okay, welcome everybody. I will be putting a bit the context, the ground for the presentation that Enrico will be giving today. You will see that our target problem is the use of AI solutions on safety critical systems. These are, let's say, solutions we really need in our systems because of the need of this computer vision for object detection and autonomous navigation. I would say that this is, let's say, the main problem that comes to our minds when we think on this challenge. If you think on what you have in your cars, in the planes, or I mean, in any critical system as of today, you realize that we already have AI inside those systems. But the thing is that normally this is embedded into fail-safe systems, meaning that these are functionalities that eventually, if they fail, can be disabled, and we can simply transfer the control to the driver or just disable the system to some extent. So in essence, this means that this AI software is not inheriting safety requirements. So this makes that as long as this AI software has enough quality, we can use it, which is good, but it's not what we need when we want to move to fully autonomous systems. When we move to fully autonomous systems, we cannot simply just disable for instance, the object detection and the navigation of the system, because perhaps there's no driver, perhaps there's no steering wheel in your car. Okay, so this is the challenge we have: how to make AI software to fit into the, let's see, the safety compliant development process of software. And we realize that the challenge is huge. Why? Simply because this AI software is developed normally, let's say, in the opposite manner that you would develop software for a safety critical system. So its development process is empirical, is based on data. It's not a control algorithm that then uses data. It's software that is developed using data for training. It's not correct by construction. I mean, it's not some software that is always providing the right answer. I mean, you know that there's some accuracy, some mispredictions, and this may happen. And this is something that was not conceived to happen in safety critical systems. And also the software architecture, I mean, goes against this divide and conquer usual strategy we use in safety critical systems. So the ambition of SAFEXPLAIN of the project, and I would say that we are really, really close to achieve it, is to enable the certification or qualification, depending on the domain, of AI software, in particular deep learning solutions in safety critical systems. This means that we have to adapt the development process to include, let's say, a specific process for AI software. I mean, we want to make sure that This process allows us to provide guarantees that the AI software will comply with the specific safety requirements. This was, in fact, what was the focus of the first webinar of the series. I mean, the way to achieve this is to add, let's say, a level, let's say, some levels of supervision and design. That in essence, this is something that was also presented in the second webinar of the series. Typically, we built on AI components for explainability and a specific software architectures that provide all the layers around, and then integrating a number of monitoring and diagnosis capabilities, and let's say leads to, let's say, to software architectures that have non-trivial interactions, non-trivial requirements. This will be the focus of the webinar today. Of course, this software can only run in, I would say, a complex beast delivering that performance. Normally, we are resorting to very high performance platforms with multi-cores, accelerators such as GPUs, and also AI-specific accelerators. And this brings an additional level of complexity that needs to be mastered. I mean, this is also focus of the discussion that we'll have today. And hence, at the end, what we realize is that we need some platform support, some toolset support, to support these software architectures, to manage the complexity of the hardware, to support the verification and validation process, and also to provide a standardized interface for the applications that will run on top. So as you see, there are a number of topics and concerns that need to be considered from the platform and toolset side, and this is the focus of the webinar today.
Great, thank you for that overview. So now we'll have Enrico go ahead.
Okay, thank you, Janine and Jaume, for the introduction. This third instantiation of the SAFEXPLAIN webinars is going to try to provide a high-level view of the platform-level support and toolset that is required to instantiate all the technologies and tools and methodologies that have been researched in the SAFEXPLAIN project. So as you just heard from Jaume, SAFEXPLAIN is trying to put together two at least apparently conflicting words. One is safety, and the other one is explainability and AI. The use of AI in a safety critical system has been something very controversial, but it's time now to make these two concepts to coexist on the same platform. And in order to achieve this, the two main pillars that have been explored in the project are how to bring together safety lifecycle, safety architecture, and deep learning-based systems on one side. So trying to bring all the concepts and requirements coming from the safety critical system in action in order to support execution of deep learning systems, architecture, and solutions. And on the other side is to exploit the explainability techniques in order to make the deep learning execution and usage trustworthy, and that is something that is essentially a requirement for the deployment of safety critical applications. So as we were just mentioning, these two main pillars were covered already in the first two webinars on the SAFEXPLAIN series. The first webinar was mainly focusing on the safety life cycle and safety architecture concepts, and the second one was on the integration of the explainability techniques inside on top of the SAFEXPLAIN framework. And of course, these two pillars, they raise a lot of concerns and requirements and constraints on the way that the system should be deployed and executed on a concrete platforms setup. So we identify several requirements that are actually mapping to the execution platform. With the execution platform, we are referring to the hardware and software and tools and any layers in the execution stack in the platform that is meant to execute safety critical AI-based systems and applications. So we see here in these cloud words several topics like configuration of the platform, interference between components, timing analysis, safety, different domains, segregation between components, explainability, and so on and so forth. And the way we are trying to capture all these concerns and constraints is essentially at the platform level. So in this webinar, we are going to provide a review of the main concept and that we implemented and designed it at the platform level for the SAFEXPLAIN project in order to capture the platform level requirements and the constraints coming from the two pillars, from the safety aspects and from the explainability aspects in SAFEXPLAIN. And of course, this is quite fundamental in order to support the deployment and execution of the use cases. As Janine was mentioning before, I mean, I will be trying to cover some basic aspects coming from the two pillars in order to make the platform level concern to be more understandable in the context of the SAFEXPLAIN project. But of course, if you need more details on these two pillars, then you can refer to the first two webinars on this series. I provide a link here in the slides. Please do not hesitate to get back to the two first webinars on the series. So as I said, I'm trying to provide us a very short background on the concept coming from the two pillars in order to understand what are the requirements that are coming on top of the platform. So from the functional safety perspective, SAFEXPLAIN is providing proposing an AI-FSM safety life cycle. What is FSM? FSM is functional safety management. So it's the definition of a process and tools that are involved in order to cover all essential activity in a functional safety life cycle as IEC 61508 standard. So this is a set of tools and processes and practices in order to develop a system in a way that allows to prevent errors in the specification, design, development, and manufacturing and commission of the system. So functional safety management is providing a process that is normally divided into phases. Here we are reporting example phases that are required for SEAL level 3 with high criticality application. So these phases are covering all the system development from system activities that cover the overall life cycle. And then we have different phases covering the specification, the design, the software aspect of the development, the testing phase, and the validation phase. And then the answer that we are trying to cover here, providing with SAFEXPLAIN, is the answer to the question on what happens when we are bringing machine learning and AI development into the loop here. So the development of machine learning and AI application has its own development life cycles with different requirements, different aspects from data management, model training, and model verification. And it has its own characteristic traits in terms of requirements for the specification. So in SAFEXPLAIN, we're trying to bring together these two words for the specification of functional safety management lifecycle for AI systems. In practice, the definition of this AI-FSM, which has been fully covered in the first webinar of this series, is providing an extension to the classical FSM lifecycle, which is following the traditional V model. So the integration of AI aspects in this model is essentially imposing the definition or extension of some of the existing phases, like the one for the system concept specification that is meant to cover also deep learning related aspects. But we also have ad hoc new phases that are introduced in order to cover the requirements coming from the development of a deep learning AI system. Essentially, I'm referring to these three phases here, called phases, one on data management, one on the learning management, one on the inference management. The first one is essentially covering all the aspects related to the data specification, collection for the data set and verification, and so on. The second phase is on actually the building of the model, so the design, the training, the evaluation, the verification of the model, while the third one is covering all related aspects for the conversion, optimization, and porting, deployment, and verification of the outcomes of the model. So in practical terms, this is creating a lot of specification for the process and templates and procedures that need to be followed in order to abide by the specification of the life cycle. And so it brings some requirements that are mostly living at the level of the design, development, and verification phases. And so it requires, of course, some specific verification validation support for automatic testing, for example, or to capture also non-functional requirements, including timing concerns, and have some implication on how the hardware and software stack should be configured in order to support the specification of the realization of different phases in the process and the assumption made, which also implies that we need to have some observability over the system execution. And what is the main aspect coming from this specification is that we have some elements that needs to be complemented by mechanisms that needs to be deployed at runtime, that we call what we call operational fusor aspects in the AI-FSM lifecycle. Essentially, at operation, we need some runtime mechanism to support the assumption made by the life cycle. And this aspect includes some traditional functional safety mechanisms like redundancy or diagnostic, for example, that are meant to capture random and systematic faults in the system and to master the complexity that arises from exceptionally complex hardware and software systems, and providing solution, for example, in terms of segregation, interface control, deployment of mixed criticality systems on the same platform, and the utilization of different hardware resources, for example. But it also has some AI deep learning specific traits, specific features. For example, we are meant to capture at runtime the insufficiencies of the DL model coming from performance in terms of performance inefficiencies or model inaccuracy, uncertainty that are inherent to the model, for example, and also to support explainability solution for the deep learning. All these AI-specific traits are meant to support and to provide the necessary degrees of trustworthiness for the deep learning solutions. What in practice this translates into the definition of functional safety architecture that needs us to be supported in the functional safety SAFEXPLAIN stack. The architecture is providing essentially a set of architectural archetypes that need to be implemented into different scenarios. These are essentially instantiation of different techniques based on, for example, diverse redundancy at the software level, and inclusion of supervision blocks in order to control and supervise the execution of the AI component, and a set of techniques that fall into multiple layers in the diagnostic and monitoring support for the execution of the system. In practice, this brought to the definition of a set of safety patterns. The safety patterns are specific instantiation of architectural archetypes in a way that allows to address different degrees of criticality in the usage of AI in this type of application. This can be done incrementally. So essentially, we have been defining 3 safety patterns. The first one is let's say the easiest safety pattern from the AI perspective, where the AI application is not meant to provide any critical decision or steering the execution of the system, but is kind of providing assistance to the user for safety and related functionalities. So in this case, we will have all the traditional functional safety mechanisms in order to cover all the risk related to systematic and random faults. And of course, all the risk coming from the integration of the application of on a complex multi-core processing system on chip platform. And as you see here, the deep learning component is going to be not very critical from a standpoint of functional safety requirements. And then we can move to a more constrained scenario in safety pattern 2, where the deep learning component is actually providing interaction with a human operator in functions that are not directly related to functional safety, but can be potentially affecting a safety function, for example, by complementing a decision process for using the result of a deep learning model. In this case, we are rendering this in orange because we are injecting new criticality related to high AI performance insufficiency, for example, and all the risk factors that are related to the usage of AI solution in low and medium integrity levels application. In this case, we still have we will have a new functional safety requirements, but still at a level that is not exceptionally critical for the execution of the system. In safety pattern 3, we are going to a more challenging scenario where the deep learning component is responsible for steering the system, so providing autonomous AI-based decision and actuation. In this case, all the AI subsystem is also extremely critical from the standpoint of functional safety. So again, we are going to deal with the same type of risks that we've been introducing safety pattern 2, but with a higher level of commitment, because all the risk factors are now related to high integrity level in the certification of the system. This part of functional safety architecture, by the definition of safety pattern, is meant to have some support at the platform level in order to deploy efficiently and correctly the safety patterns on the platform, to enforce the hardware software configuration that is required in order to support the safety pattern themselves, and the integration of the explainability solution inside the pattern. And of course, as part of the diagnostic and monitoring layer support, we need to provide runtime monitoring features and cover observability concerns and timing concerns of the platforms. And, conversely to the first set of requirements coming from the functional safety management part, all these aspects are mostly related to the runtime execution of the system. So they are living in the runtime operational part of the platform. Then moving to the second pillar on explainability AI. Explainability AI is this set of processes, algorithms, and methods that allows humans to understand and trust the results and outputs generated by the machine learning algorithm. So essentially, these are all the mechanisms and tools that are, in this case, necessary in order to provide trustworthiness on the outcomes of a deep learning system. And again, here we have SAFEXPLAIN explainability AI methods that apply to the two different layers, one more on the system development, design, development, and testing phase, and the other one at operation. In the first domain, explainability AI solutions are meant to cover to enable all the new phases in the functional safety lifecycle that are related to the definition of AI models, data management, learning, and inference management. So at the level of data management phase, explainability AI solutions are essentially in the definition of data explainers that are going to assess and verify the data set, whether it meets the requirement, it covers at least the baseline known condition that we are going to capture at operation. And while on the learning management and inference management phase, we are meant to deploy model explainers. On the learning management phase, we are providing solution for explaining the model at design time by construction or by capturing evidence on the learning phase. And all these solutions are meant to reduce the epistemic uncertainty. Epistemic uncertainty is one of the different types of uncertainty we have in the AI models. This is related to the model itself, maybe to capture insufficiencies in the way the model has been designed and built. And this phase, the model explainers are meant to capture the baseline nominal behavior of the AI model at runtime. On the inference management phase, we are mainly focused on model conversion optimization and on the verification of the inference output of the AI model. So all these elements are requiring some specific set of tools in order to cover data explainers, for example, the model explainers. These tools are covered by one of the outcomes and tools from the project, which is called explainable, explainability library. Is essentially something that is used at design, development, testing phases. And so it doesn't require specific support at the platform level, but we will see that it injects information and inputs in order to support explainability AI at the level of runtime. At the level of runtime, we are meant to integrate the explainability AI solution on top of the functional safety architecture, which means inside definition of the safety patterns. And in safety patterns, we have at least two aspects in the functional safety architecture that are meant to accommodate the explainability AI solution. One of these is the model supervisor, which is the component, the element in the functional safety architecture that is meant to check the behavior of the model. So in this case, we're going to deploy solution tools in order to check for anomaly detection in the input and output of the models and on the model behavior itself. For example, to an implementation of surrogate models for consistency checks in the execution of the model, or some methods for estimating the epistemic certainty in the model. And then at the level of the decision function is essentially one component in functional safety architecture, which is meant to take in input model prediction and supervisor score from a set of redundant models and or surrogate models, for example, and to provide an output also as a unique decision based on ensemble and a trustworthiness score. All these requirements are meant to be covered at runtime by a different set of tools. In this case, this first part of the tools like for the model supervision are meant to build on top of the outcomes of the explainability library, of the results of the learning process, for example, or the explainability information that can be retrieved offline at analysis time and design phase. These are used in order to implement the specific tools and solutions that are deployed on top of the platform. In this case, we talk about a different tool, which is called DLlib, Deep Learning Library, which is essentially working at runtime and providing all the necessary solution for the explainability AI on top of the platform. So we see this was, sorry, maybe a fast, but try to cover at least some of the basic concept on the two pillars in order to understand how the system level platform is meant to capture them on the target hardware and systems of the stack. So we have all these elements are creating a very large set of widespread platform level objectives covering different elements. We need to support an integration of the proposed solution for the functional safety architectures and patterns and all the explainability AI tools and methodologies. Also, we need to offer a common layer for the software verification and the mechanisms like diagnostic and monitoring, functional testing, timing characterization that we just seen, and that are part of the requirement, often implicit or explicit requirement coming from the functional safety FSM and architecture. Also, we had to provide an abstraction layer for the system configuration. As we see in the hardware software configuration is one of a critical aspect that is appearing in several elements in the technologies provided, because we need to make sure that all the assumptions that are made on the architectural level are also enforced after we are deploying the system on top of a specific target and software stack. Also, as part of the project, we are also meant to offer a reference common stack for all the different use cases we are covering in the project that are, in fact, spanning over different industrial domains, from the railway to automotive and space domains. So what is the main approach that we followed. So we had to support, enable, and integrate on top of the hardware stack and system software a lot of let's say requirements and constraints covering several aspects. What we built, is on the concept of SAFEXPLAIN middleware. The SAFEXPLAIN middleware is something that lays in between the target and system software stack, and integrate a set of diverse tools and technologies in order to support all these constraints and requirements from the functional safety and explainability pillars. So now we are going to try to go into a little bit more of details on what are these platform technologies and tools. I will go first over the hardware platform in SAFEXPLAIN, and then provide an idea over the main concept that we try to implement as part of the middleware and how we actually realize that on top of the platform. Then we are providing some highlight of the platform level support we are providing for safety patterns, platform configuration, observability concerns, timing characterization, monitoring, and verification and validation support. And in the end, I will close with a review over the platform support, trying to bring all the pieces together in the actual instantiation of the technologies. So in SAFEXPLAIN, we had to select a target platform. So we were looking for a platform that were able to address all the computing requirements coming from the complex AI-based systems. And the NVIDIA Jetson AGX Orin was a candidate platform. It can provide a large amount of operation that can support quite complex application for autonomous operation decision-making. It brings a large amount of computational power with NVIDIA Ampere GPU, several clusters of ARM Cortex A78 CPUs, and they also brings a set of ad hoc accelerators for deep learning with NVDLA or vision application, and also dedicated video encoder and decoders, high-speed IOs, and 2 gigabytes of memory that's been extended with 2 terabytes with NVMe. This has been selected because of the size in terms of computational power and power consumption, and was assessed to be a reference platform for the domains that was considered in the project. So as you see, this is a very small platform, but it's not so simple. So it equips 3 clusters of 4 cores each with different layers of shared caches, shared architecture, and we have 2 GPU with a streaming multiprocessor, again with shared caches, shared resources, a lot of ad hoc accelerators here, 2 NVDLA, a PVA, and the encoder shared across all the elements of the platform, and a memory controller that provides access to the main shared memory. See, the complexity of the platforms, while it's good from the computational perspective, because it allows to accommodate all the requirements that are coming from the execution of the AI application, but also to support all the mechanisms that we are bringing on top of it for the supervision and control of the outcome of the deep learning part, for example. But on the other side, this complexity also poses a hurdle for some functional safety aspects related to the certification and verification of the system that we will go over this later in the presentation. At the level of the software stack, and the NVIDIA Jetson Orin comes with a adapted version of the fully fledged Linux kernel. Is providing essentially an Ubuntu 22.04 instance, slightly adapted to the target. Is based on the Linux kernel Tegra 5.15. It also provides a full set of libraries that support the development and execution of AI application, from TensorRT, PyTorch, Vulkan library, QDNN, OpenCV, and CUDA libraries. all that is necessary in order to deploy a functionally rich application based on machine learning on top of this platform. Also on this aspect, let's say that this wide support for AI application is of course a pro for our setup. On the negative side, we see that the execution of mainstream operating system as opposed to real-time operating system can create some, bring some criticalities, again, related to function safety concerns because of the complexity and huge size and dimension and type of services and noise that may arise from this type of system software. But we are going to go over this later in the presentation. What is the concept of middleware? Middleware is something that we are meant to bring in between the hardware and software, simple software stack and the application software in order to capture all the requirements that are being arising on the application level, on the functional requirement, performance requirement for the AI application, or another set of non-functional requirements including timing and interference when applying on when executing the multi-core setup, or any other non-functional aspect related, for example, power consumption or segregation and so on and so forth. And of course, we are the requirement coming from the explainability AI methodologies and tools that are going to be deployed on the DL components in the platform. So with the middleware, we are meant to provide an abstraction layer that allows to offer a set of functionalities to the application and support the function safety architecture, support all these wide set of requirements coming from the XI part of the project, and also to manage the complexity that I was just mentioning, that is coming from the combination of the hardware and system software complexity and the complexity of the application that are exploiting the deep learning solution. So the concept of SAFEXPLAIN middleware is meant to provide a way to integrate all the technologies and methodologies and tools on a unique layer and provide a simplified API to the user for the application. So the middleware is meant to operate at the two layers, at design time and operation time. At design time, we want to ensure the correct deployment of function safety architecture concepts and safety patterns by design, by construction. We want to support testing automation, by verification and validation, and enable all the diagnostic and monitoring requirements coming from the function safety architecture. At operation time, we want to enforce the hardware and software configuration that are designed and implied by the functional safety and safety patterns on the, for example, in terms of performance and segregation of the different components in the system. We are providing all the support for the online monitoring and diagnostic, and we are supporting control of the impact of timing interference in the execution of the critical part of the application, and all integrating all the AI solution and tools that are meant to operate at operation at runtime. What are the main aspects here? So the core aspects that we try to cover with the realization of this middleware concept was that we were considering that we are meant to provide a large set of functionalities. We are meant to support an architectural level concerns, and we want to enable integration of a large set of software libraries and tools. And after a careful examination, we decided to build our middleware on top of ROS2. ROS2 is a well-known DDS-based middleware for distributed application. It's been selected because it's already a wider adoption in several domains for the definition of highly modular application and scalable application. It's based on a very simple functional semantics on a publisher-subscriber model, and it can cover local applications as well as distributed ones. and provides some interesting feature in terms of native support, for example, for some platform level functional safety requirements, for example, for status manager of different components or health managers that are native from ROS2 Humble's version onwards. And also it supports some automated functions for testing, including testing framework, automation, the inclusion of assertion for online monitoring of the code. And it's been considered as a very nice starting point for building the services and elements, integrating all the elements that are in the SAFEXPLAIN toolset and methodologies. In practice, what does it mean using building on top of ROS2? Essentially, the middleware is essentially providing an extension of simple ROS2 nodes. It's like definition of a wrapper, a specialization of these nodes by providing a set of functionalities and features that are not in the standard definition of a node. All these features are meant to cover all the requirements coming from the functional safety specification and architecture. So we have a specialized node for the application, specialized set pattern for the communication and data flows in the system, and the definition of the specific monitoring mechanisms that are required in terms of realization of the functional safety architecture. So essentially, we are defining a set of node archetypes, middleware nodes that are extending the baseline ROS2 node with specific elements. So a middleware node will build on ROS2 health and status manager features, but will provide a simplified API for the definition of components in the application. So essentially, we are getting rid of all the configuration that is not required at the level of the nodes. We leave just the user the burden to fill in this node with the semantics that is required by the functional part of the node. All the other elements are dealt with at configuration time. And of course, as part of this node, we are also providing native and transparent support to the user for profiling and monitoring the execution of each node. And we can provide, by design, some definition, implementation, instantiation of the nodes to realize what have been defined as the safety patterns in the functional safety architecture part. And interestingly, this leaves room for the definition of model-driven engineering approach in order to generate by design, by construction, complete system based on the instantiation of safety patterns. At the level of the configuration, as I say, we are dealing with some other aspects that can be controlled in a centralized way. So we build on the ROS2 launch parameters file, and we control the profiling of nodes by, for example, enabling, disabling the profiling, or by controlling the way the execution is of the nodes is actually happening at runtime on top of the deep software stack. So we can provide a fine-grained mapping of the nodes on top of operating system level threads and processes. What is a pivotal concept in the platform level support? As we were just mentioning, the middleware layer allowed to cover all the system level aspects related to functional safety by allowing the definition of the safety pattern by still preserving some degree of freedom and modularity to the system designer. So we will have a set of mandatory nodes and components. But we can allow the user to provide a user-defined node for application semantics just by abiding to a simple interface that complies with the requirements at the architectural level. And we are offering this multi-layered monitoring diagnostic approach that goes from the ML components to the ML model itself and the system level diagnostic and monitoring. We are supporting specifically archetypes for the deployed configuration. So we have a configurable predefined setups based on definition of safety patterns elements and with some minor configurable options. and we have support for the testing and integration of the all elements, unit testing, integration testing, and all the other activities coming from the VAV support. And we allow the integration, easy integration of all the technologies and tools we have been developing in the project. A library for timing profiling, approaches for the timing analysis, characterization, and control of timing interference, for example, and deployment of the explainability methods and tools. And also, we are offering a common software environment for all the use cases that allow the tools easy deporting and the evaluation assessment of the use cases. Last but not least, the middleware is implemented, providing support for the multi-language application. And as it's based on ROS2, is highly portable to different setups. So in this case, we have an instantiation on top of the specific software stack and hardware stack in the project, but is easily portable to different setups. So let's now start moving a bit into more details and look at how the concept of the platform level may support the instantiation and realization of some of the concept and requirements from the functional safety and explainability AI layers. And when it comes to the safety patterns, I say these patterns provided by our project are meant to extend and combine some common patterns that are coming from traditional functional safety. So essentially, these patterns combine the concept of diversity and redundancy, but at the software level, not only at the hardware level, and they are essentially provided as a specific set of nodes and components in the functional safety architecture. So we are going to have different types of patterns. Here we are providing different types of deployment of the concept of diversity and redundancy from the simple system, where we have only one subsystem, a set of subsystem element, and a diagnostic part controlling the input and functioning and output of the model. Then we may have double redundancy with two different redundant and diverse subsystems with different diagnostic support, and then we can take a decision based on the outcome on two components out of two. And then we have a more larger system, more critical system, where we have triple redundancy, for example. We can take a decision based on the outcomes of two subsystem elements out of three. Which is the pattern that we want to instantiate at the platform level depends on the actual scenario of the application and the level of the involvement of the AI component in the decision process. As we were mentioning before, the higher is the criticality of the AI with respect to the functional behavior and the decision process, and in the system, the higher the more stringent and the more powerful is the set of safety patterns we need to deploy at runtime. Let's have a look here at one of the specific instantiation of safety pattern in the functional safety architecture. We are referring to safety pattern 2, where the AI ML constituent is not directly affecting functional safety, a critical safety critical function, but may partially or eventually affect the decision process. In this case, the safety pattern is enforcing the diverse redundancy at the AI ML constituent level. So we are going to have two redundant model making and providing an inference on the same problem, but we have diversity, and diversity in this level can happen at with different incarnation. Can be diversity on the input, diversity on the model itself, diversity on the way the model has been trained, and so on. And we have, as part of the diagnostic and monitoring layer, we have a supervisor block. Supervisor block is including L1 diagnostic and monitoring mechanisms that are classical, traditional functional safety mechanisms, making checks on, for example, the input and output and functioning of the components. And we have specific diagnostic elements that are embedded in a supervision function, which is instead specifically related to the AI-ML part of the system. And we have a decision function, making decisions based on the outcome of the models, random models, and the outcome of supervision function. Then we have an own AI subsystem, which is also contributing to the, in this case, is driving the functional behavior of the system. We have L2 diagnostic monitoring mechanism, and eventually at the platform level, an L3 diagnostic monitoring mechanism. So we have the outcome of the AI component that is potentially contributing to the decision function, which is anyway taken by the safety control based on the outcome of the non-AI system. At the middleware level, we have an implementation of the same pattern by the definition of the set of components, by providing the definition of nodes, where you just need to plug in the functional part, the semantics of the nodes. So all the communication, all the let's say fixed element in the system, like the monitoring part and the way the monitoring part is correlated, linked to the execution of the nodes, is already fixed. And what is left to the system designer is to provide the logic for the supervisor, decision function, and the control. On the hardware software configuration side, we see that we have several requirements coming from functional safety. In this type of system, we have, as a pro, we have the complexity of the platform, the rich computing elements from accelerators, cores, and GPUs, is providing all the necessary performance requirements to meet the execution requirements from the AI components. But on the negative side, the complexity of the platform is arising some concern for the verification practice, especially for the timing dimension, because of the contention arising when multiple elements in the system are trying to access simultaneously the same set of shared resources. This same concept is very well acknowledged as in functional safety standards and regulatory documents. It's called mentioned in freedom from interference in the ISO 26262, or correspond to the concept of interference channels forecasted to MC 2183 for the avionics. And the focus here is on providing a right way of configuring and deploying the system software on the hardware side to promote segregation between components and to meet the performance requirement at the same time. This may be sometimes conflicting objectives. So as part of the project, we went over the analysis of the classification of the sources of interference at the hardware level, identification of the mechanisms available in order to control and mitigate this interference, to identify what are the deployment configuration available and ways to instantiate and support them at runtime. And at the practical level, we've been working on the identification of these sources, then classification of them in terms of where they are negligible or can be boundable, or they are critical to execution of the system. At the software level and the hardware level, the software level, we've been looking at the noise, for example, of the operating system. I was mentioning before that the support provided by the general operating system, the mainstream operating system, like the one provided in this platform, is very nice from the library perspective, but also provided some challenges in terms of analyzability of the system because of the timing interference and some time noise it may arise on and may bring on the application. And we've been analyzing them. We'll be applying the real-time patch in order to enforce priorities for real-time priorities for part of the system, the most critical part of the system, and to reduce the variability coming from the system calls in the operating system. And it's meant to support the assumption from the safety pattern and the performance requirement in the platform at the same time. So we've been identifying the hardware level, the source of timing interference, the platform, by analyzing the architecture from the available manuals, but also doing some empirical activity, doing some type of reverse engineering in order to confirm the expectation and assumption of the platform being defined. Domain of sharing of the different hardware resources in order to understand the level of noise interference that may come from sharing these type of resources. And we have been looking into the mechanism available in the platform based on essentially providing some degrees of partitioning on the shared resources, but also trying to leverage on how the different components in the system are executed in the platform. And this, of course, need to be done and by considering what are the requirements coming from the application semantics and, of course, the functional safety concerns themselves. So we've been identifying a set of mechanisms that can be deployed on this particular setup, including, for example, the partitioning, some of the cache layers, specific configuration in the platform, and also some of mechanisms that can be enforced at the software architecture level, for example, by defining which components are going to execute together or on the same set of computing elements. So here the problem is to provide a nice way to map the components in the system, all the elements we have in the safety pattern, in functional safety architecture, on top of the software and hardware stack. So which means to understand how to map all the components we have in the middleware layer on the different runtime entities at the operating system layers, whether they are processes or threads, and how these the latter are mapped on the different components, say cores or accelerators in the platform. So we come with a catalog of solutions that are meant to be selected in order to at the deploying time based on the application and the safety pattern requirements. But also, as we keep in mind, what is one of the main requirements on this type of system is to keep up with the performance requirements coming from the deep learning solutions. For example, on a platform configuration, we are going to identify what are the island of components that can be executed together on the same set of, for example, on the SIM cluster here. What is the power mode? What is the partitioning scenario we want to enforce? What are the accelerators we are meant to use on the execution? And at software configuration layer, we are going to, of course, apply the patch in order to remove the noise of the operating system. We are going to deploy a fine-grained allocation on the cores and a different allocation of different threads and priorities in order to make sure that the requirements in terms of execution on the system level or the software level are enforced on the platform. And of course, we have a mechanism that we are going to deploy in order to support the protection for multi-core interference and timing noise for those critical nodes that are taking care of most critical in the execution of the AI component, but also on the non-AI component. This includes a mechanism for controlling interference and to protect, for example, the decision function and safety control, which are the most critical part in this pattern, in the safety pattern too. At the level of platform, we also were mentioning before that we have some observability requirements. So in order to provide evidence that we are complying with the constraints coming off at the hardware and software layer, we need to have access to be able to observe how the execution actually proceed on top of the platform. Or this, we can rely normally on a set of hardware events on the platform that can cover various degrees of observability with different scopes. And the information we can retrieve from the execution on the hardware by configuring and reading hardware events is going to be useful at analysis time in order to support the evidence for example, the configuration, the safety patterns, or the performance assumption requirements and expectation we have. At runtime, also to deploy monitoring mechanism to intercept deviation from the expectation and to timely react to those deviation. So in this respect, we've been providing a tool in SAFEXPLAIN, which is called PMU-lib, Performance Monitor Unit Library. Is a lightweight configuration and collection library for hardware events. Is allowed to perform the timing and interpretation on the platform and to validate all the requirements on the safety patterns. It's based on a two-layer design. Part of the platform is essentially platform specific because it's tailored on the ORIN. But part of the platform or the library is generic, So it's based on the Linux stack, so it's highly portable. And we offer these different observation scope with the library at thread level, process level, core level, so we can gather events at these different scopes depending on the usage we want to make of the information retrieved by the library. We are covering more than 130 events at different layers in the hardware architecture, with the cache hierarchies, with the connection from the nodes and the GPU with memory. And this is fully integrated in the middleware. We have, as you were mentioning before, we have capability to perform node-level profiling without asking any configuration on the user, except for enabling and disabling the profiling. And we are providing also user-level support for timestamping, which is useful for coarse-grained assessment of the performance of the application. So PMU lib is a tool that is enabling other technologies that are going to go briefly next, or CGuard for timing interference control and SK for timing characterization, but it's also useful for validation the requirement we have from the hardware and software configuration. For when it comes to timing characterization and monitoring, we have two main tools here, SK and CGuard. So the timing analysis of deep learning-based software in these types of complex architecture is challenging. It's challenging for two reasons. Essentially, on one side, we have the complexity on the hardware that is bringing, for example, multi-core interference or difficulties in analyzing the behavior of the platform without deep knowledge on the internal of the platform, because these internals are normally not disclosed because of IP reasons. And on the other side, we have the complexity of the software solution. We have interaction of different components. We have the complexity of the deep learning method itself. And the worst case scenario in this case for the integration of this type of function on this type of software is difficult to characterize. And the characterization of the worst case scenario is a fundamental concern for the safety critical system. So the timing characterization of this type of system is becoming recently more and more popular, and acknowledge that it is possible to go away from the traditional concept of worst case execution time for timing characterization, and moving from a single discrete value, which is often difficult to find in this type of setup, to the concept of a probability distribution of execution times, which is called probabilistic WCT. So the timing bounds and probabilistic bounds are, in this case, derived by applying some kind of statistical procedure on a large set of data collected on the platform, on focusing on the high quantile of this probability distribution in order to derive bounds that can be assumed and enforced at the runtime. So the strategic objective in SAFEXPLAIN is to provide support for the timing concern in two aspects, in two dimensions. One is on the timing characterization of the behavior of the AI-based solution, and for which we are resorting to the SK tool, and for runtime support for the interface control. That is something that we need to capture in order to abide by functional safety concern. And for this, we are going to rely on top of the CGuard tool. For the time prediction method and tools, the time characterization or Riolin is complex, with some massive parallel architecture with high degrees of shared resources that brings a state. So the state can be changed by any of the application and processes running on the platform. This implies the execution time of an application is essentially more large distribution of execution times, larger than a single value. So that's the reason why we are going towards the use of statistic analysis tools to produce WCT estimates. And one of the preliminary concerns we had to capture here is that as this statistical analysis is based on collection of data, the variability across runs here is something that is we need to cope with. And especially how this variability is affecting the way we can observe the execution, how this variability affects the values we can have on hardware events. And all the hardware events, what makes it even worse is that all the hardware events, we know they belong to a probability distribution, but this probability distribution is impossible to observe in practice because platforms do not allow to collect all the hardware events at once. So it is not possible to observe distribution. But what happens, we need to bring together anyway these hardware events, and in a way that is correct and robust. So collecting hardware events from different runs, but being able to put them together in order to use the information in a collective way. So we know they belong to a unique distribution. So we apply a statistical approach called match in order that builds on the multivariate character distribution to model the relationship between the hardware events monitors, and we can provide a single outcome as a full single set of hardware events that preserve the dependency happening between hardware events as if they were measured at once. This type of information that's used to feed the probabilistic timing analysis that we see. This type of system, they may exhibit timing behavior that is quite away from the timing behavior of a simpler traditional system in safety critical applications, where the timing behavior tends to be close to the same values with very low variability. In this case, we can have use variability. We can have multiple distribution happening concurring to execution time to explain the execution time of a program. And while the majority of works in probabilistic timing analysis within extreme value theory, we know that the extreme value theory is weak when it's time to analyze the type of mixed distribution. It cannot be effectively applied, leading to underestimation or overestimation of the time behavior. And for this reason, we went for the application of REST-K methods. This REST-K methods is based on the Markov inequalities method for timing analysis. That is coping with the risk of overestimation that is inherent in Markov inequality methods by restricting the value of the K parameters. That allows to have a very tight upper bounding of the distribution in the extreme case. It has been shown to be particularly effective for this type of distribution, always providing a tighter bound and safer bound with respect to simple AVT-based methods. From the time interference standpoint, we're meant to deal with timing interference. We see timing interference that won't happening at runtime because of the sharing of stateful hardware resources. We know the degree of interference may vary depending on the type of shared resources the program under analysis is using, coming from negligible to really penalizing. And we know that we've been looking into hardware configuration, software configuration that allows to kind of control or mitigate the amount of interference that can happen at runtime, and as part of the safety pattern implementation. But the full freedom from interference is hard to achieve on this type of system. It's impossible to achieve. So the goal in our goal was to demonstrate that it's possible to have a bounded independence from interference, so that we can provide a bound on the residual interference that can happen at runtime. And this is a necessary element for the simplification argument. So we are following a twofold approach. At analysis time, we are providing offline scenario-based analysis in order to understand the sensitivity to interference from application based on the usage and deployment of ad hoc templates of a program that are running in parallel with the target application. While at runtime, we are building out monitoring mechanisms that allow to ensure and enforce that a shared resource is not assessed more than a budget, which means that the impact coming from sharing those resources is not going to be to exceed the budget or the expectation made at analysis time. We call this mechanism tool CGuard. CGuard is a flexible practical approach in order to build with monitoring the execution of task. So as long as task is executing, is having some impact on the interference that may arise on the system. For example, here we have core one that may executing, while executing may be affecting the usage of the execution of another critical task in core zero because of the usage of shared resources. With this type of mechanism, we actually embedding a threshold and mechanism where when we see at runtime that is task and program executed on core one, which is deemed to be non-critical, is actually, I think I need to speed up a bit, is actually exceeding the threshold. We are triggering a mechanism that is preventing the non-critical tasks from further executing and further interfering on the execution of the critical one. And we are going to use we are using a monitoring mechanism that is based on middleware nodes that allows to enforce observation period between which non-critical tasks are allowed to execute as long as they do not exceed these threshold values. And after that, they're put on throttle till the next period when they are replenished for the budget of execution, or till the critical task terminates its execution. In order to select the threshold selection, we are meant to cover what are the non-observed scenarios, and these thresholds, of course, are application dependent. At VAB support will be very quick here. Essentially, we are building on a lot of ROS2 functionality, unit testing based on G-test for code coverage, component testing framework provided with ROS2. We are using ROS launch in order to support the testing based the capability to set up the environment scenario in the application, and ROS back to replay and replicate the known data for the testing. The testing is usually based on runtime data for log parsing and instrumentation with fault injection, assertion, and we are also providing support for scenario-based strategy, which is part of the AI-FSM lifecycle. So in short, our view here. So I say we are trying to bring on top of the SAFEXPLAIN platform to accommodate a large set of requirements on the platform, the system, on the hardware platform and a system software stack. We are covering this with a middleware stack, which is building on ROS2, is providing a way to instantiate safety pattern by design, to provide automatic status support and VAV support for generic VAV tasks. And we are providing runtime monitoring mechanisms with different layers, and the L1, the L0 for the model, L1 for the component, and the 2 for the system level. We are providing solution for the other configuration, software configuration, how to map the different elements also at runtime in the different software elements at the operating system and hardware element in the platform. And we are integrating the lib solution in the monitoring part, and the supervision function, and the supervision function also exporting information coming from the explainability lib at design time, and DLlib functionality and decision function. We are also deploying REST-K for profiling the execution of the different nodes based on the user of the PMU library, and allows also the enforcement of time interface control with CGuard at the level of single nodes on decision function and safety control, which is the most critical part in the safety pattern. And all these elements together, they find in the SAFEXPLAIN middleware a way that easy integration and modular development of different type of systems. We see this, the interoperability of the technologies. We see all this set of tools and methodologies is quite consolidated in the software stack, but all these elements can also have an independent life that can be deployed independently from all the software stack we have here. They build on some common features. I see we are building here on Linux-based environment on ROS2 and on specific technologies, for example, in explainable that find a specific incarnation and instantiation DLlib that can be deployed in different setups. So in terms of general stability, all these platform level support can be extended. Depending on the hardware and software setup, we may have a limitation to what can be provided, or even improvement extension of what can be provided. ROS2 is in particular ensure an exceptionally high level of portability of the solution, and we are able to cover 3 different use cases from diverse industrial domain. So we have a use case from the railway, automotive, and space, or each one with different criticality level based on the severity of the consequences in case of misbehavior of the system. And what we are going to provide soon is almost ready, is a technology demonstrator for all the elements that have been showing you today. It will provide a score of open source element, and all those elements that will be in open source anyway will be fully documented and should be ready. So stay tuned for this demo to look at these technologies live. Thanks a lot for your attention. I think I went a bit over the time that was allowed. Sorry about that.
Hi, great. Thank you so much. No, don't worry about it. I actually raised my hand by accident. Great. Thank you for that. And we actually have a question. So if you don't mind, we'll jump right into that. So the question is, isn't using probabilistic approaches, PWCET, a problem for FUSA certification?
Yes, yes. So this is a highly debated aspect. Yeah, yes. I mean, this is not fully accepted yet as a methodology in order to go through certification. But what we are doing in SAFEXPLAIN is not to focus only on these aspects. We are providing a kind of an holistic approach where we are still applying traditional methods, for example, for timing, characterization, but we are also advocating for the usage of these innovative approaches that are anyway considered now one of the most practical way to deal with the complexity of this system. So what we can accommodate in the SAFEXPLAIN platform and stack and methodology is traditional functional safety certification approaches, so also traditional approaches for timing verification, but we are enriching this set of elements with other elements. This one, for example, on probabilistic characterization, and is going to be anyway an element on a system that is building on kind of a safety net in order for all these requirement and assumption that we are making on the timing or non-functional behavioral system to be anyway intercepted at runtime, any misbehavior or divergence by the diagnostic and monitoring support. So for example, now even at the system level, at the middleware level, the nodes in the middleware level, they do have also mechanisms in order to monitor the execution, for example, monitor the execution within the deadlines of each component. So in short, yes, this cannot be at the moment the only solution that can be provided, but can be part of a more elaborated and holistic solution.
Great. Thank you. And so I have another question here. So the concept and building blocks of the SAFEXPLAIN platform seem to support some degree of modularity and portability. Are there any minimal portability requirements on the hardware and software stack?
Well, at the moment, I would say no. There are some minimal elements that we think that are almost available in every type of farm platform. Starting from the bottom layer, we need to have some degrees of observability, controllability on the hardware in order to make sure that we can enforce the hardware and software configuration that are assumed, for example, by the configuration that we have through the safety patterns. So we need to have observability in order to make sure that the safety patterns are correctly and efficiently deployed on the platform. We need to have hardware configurability in order to bring the necessary degrees of segregation between the components in the functional safety architecture. But this is part of I would say, the platform and software stack selection process. So, you know, the more you are selecting a platform that is providing this type of minimal support for observability, configurability, the easier will be for you to deploy your system in a way that can undergo at some point certification process. And just to add something on this, all the methodology and tool from the tooling perspective we have been presenting today are building on, in this case, on being deployed on the stack that is including a Linux distribution version and ROS2 version, RS2 installment. And as such, you know, the degree of portability is very high. At least we demonstrated that we can have an instance of these technologies on top of very, very flexible and portable setup stack.
Okay, great. Thank you. And the last one that I see so far, maybe someone else will get inspired. But with functional safety concerns being a central element of the project, how is the proposed platform supporting qualification and certification? Is the platform itself amenable to certification?
Okay, so we need to distinguish between several aspects here. So we have the platform, hardware platform itself. This is an aspect of certificability of the platform that is highly debated. What we are providing here is a proof of concept deployment implementation of a set of technologies and methodologies and arguments and processes that should support, as meant to support the certification. As part of the project, we are exchanging information with several collaborators and partners. For example, we have an exchange information with TOV in order to build a certification argument. And so we are already trying to advance on these aspects. Of course, there cannot be certified platform outside as the outcome of this project, but is for sure something that we consider in reach of the project.
Okay, excellent. So I don't see any more questions, but if somebody is inspired later, I'm leaving the email here for the project. So please reach out if you're interested. Also, the project website and the LinkedIn is where you have the most up-to-date information. Thank you so much, Enrico, for your insights, and Jaume too, who's here. And thank you to everyone who attended. Once again, the webinar has been recorded and will be online in the coming weeks. So thank you very much.
Thank you.